the Python Lab 3, what I'm gonna do is I'm gonna solve two of the problems that are on the lecture 10. I'll skip this, the derivation of the weak form. This is the elasticity problem, which is the one that I'm gonna be solving. And as you know from the weak form, we get a definition for the stiffness matrix, and in this case you can for the linear elasticity problem, you can work out that the stiffness matrix is just like the truss problem, so area times Young's modulus over length, and then 1 minus 1 minus 1, 1. Again, this is not necessarily the case for other problems, but for this particular problem, when you plug in the derivatives of the shape functions and you integrate, then you get with this final stiffness matrix. And then the force vector, it really depends, as I discussed in class on lecture 10, that there are two simplifications. In general, it might not be, you might not be able to simplify. It all depends on what that B term looks like. But if the B is linear, then all you need to know is what is the value of B, the body force vector at the beginning of the element and the body force vector at the end of the element, and then you can do this matrix vector multiplication, and that will give you the force vector for the element. Again, those two depend on the particular problem, as I showed in class. It can be simplified for the constant B, or it can be simplified for the linear B, and here is the solution. In the homework, you have to redo the stiffness matrix and the force vector derivation, because you might not, this might not be the final force and stiffness matrix, so you have to derive it. Again, this is only true for the linear elasticity problem with linear B, and again, this is also only true for the linear elasticity problem. That's, so you'll have to derive it for homework 3. And so the problem that I want to show is this, where we have this bar of length 2L, which is fixed at the left, and then it has some traction at the right end. We are given the traction here, and we have the body force is C times X, where you can see that it's going to be linear over X. So this is the problem that we want to solve. So let's go ahead and solve it. I have my Python notebook here. I need to define the parameters, so actually I'm just going to copy those from, this is what I did last year, or last time I taught the class. So let's just assume that the length is 1, that this is C, the area, the Young's modulus, this is the traction at the end, and then I'm going to create my mesh. I'm going to use 4 elements, 4 nodes, 3 elements, and these are the coordinates of the elements. So the first node is going to be at 0, and then I'm just going to split evenly the 2L into the 2L over 3, 4L over 3, and then 2L. And then the elements are, the first element is 0, 1, then 1, 2, then 2, 3. If you want to check whether or not this mesh is correct, you can always just plot to make sure that the this scatter of the X is in the correct place. I won't do it. Let's just go straight into what we need to do. So at the end of the day, what we will have is a stiffness matrix per element. So let me write that here. So we have definition of Ke, which is the stiffness matrix of the element, and so we have that, and then we also have the definition of Fe, which is the force vector for an element. So what we need to do is we need to loop over elements, get Ke and Fe for each element, and then assemble into the global K, so the global stiffness matrix and the global force vector. So that's what we need to do. So you can see already that this already tells me I have to loop over elements. For every element, calculate the stiffness matrix and the force vector of that element. So let's do that. For I in range, the number of elements, so I'm going to loop over the elements. For each element, I need to find KE and I need to find FE, right? So what is KE? KE is the area of the element. All the elements have the same area, so I just need the A0, so the parameter A0, because all of them have the same area, times the Young's modulus, which again is the same for all elements, over the length of the element. Now this LE, that one I still need to calculate, so I'm going to put it up here because I need to calculate what is the length of the element, times the matrix minus, 1 minus 1, and then minus 1, 1. Right? So this is the stiffness matrix. And the only thing that I don't know here is going to be this LE. So I still need to be able to calculate that LE. I'm going to leave it up here for a second. Then for the force vector, like I said, the B, what does the B, I don't have it here. I have the C. But B is, okay, so let me just put here for force vector, recall B equals Cx. So B is linear, right? So B is linear. So all I need is the value of B at the beginning of the element, which is B1, and value of B at the end of the element, which is B2. All right, so B1, because B is Cx, B1 is going to be C times the beginning of the element, which is x1e. I still don't have that, but this is how I will get the B1 and B2. Right? So B1 is going to be C times the beginning of the element. B2 is going to be the B at the end of the element, which is, because B is Cx, it's just C times x2e. Okay, but that tells me that I also need to know what x1e is and what x2e is. So I'm going to put it up here. I still need to define that. But given values of B1 and B2, all I need is to follow my what I derived already, which is what is the force vector for the linear case. So it's length over 6 and then 2, 1, 1, 2 times the vector B1, B2. All right. So length of the element over 6 times, and then matrix dot product in NumPy, you have to use NumPy dot, and then the matrix is going to be the array 2, 1, 1, 2, and then that is going to multiply another array or vector, but you know, I have to use the word array, which has B1, B2, right? Okay, so this is the matrix 2, 1, 1, 2 multiplying B1, B2, all of that L over 6. So this is the same thing as I have here. So 2, 1, 1, 2 multiplying the vector B1, B1, B2, and then that multiplied by L1, L over 6. All right, so that's it. And again, really the only things that I don't know here are LE, which I still need to calculate, and then B1, B2 are here, which depend on C, x1 and x2, which I also put out here because I still need to compute those. But as of this point, I have the element stiffness matrix, and I have the element force vector. Okay, that is progress. So let's actually go here and see how we can get that length of the element in this x1, x2. For the length of the element, if I have x2 and x1, the length of the element is easy. It's just this x2 minus x1. Okay, so that's easy. So it really needs, it boils down to having x1 and x2. Where is that information? Where is the information of the beginning of the element and the end of the element? That information is in node x. I know that node x has all the x coordinates. So this, here I definitely need to go and read the node x array. Here is where I need to read the node x array. And the question is, which node should I go get the x coordinate of? right? So this is the end of the element. So I need to know what is the node at the end of the element. Let me call it N2. And then here I need to know the node at the beginning of the element. Let me call it N1. And now I need to find what are N1 and N2, right? So what is the beginning of the element? Where is that information? That information is in the elements array. So the elements array has the nodes that make up every element. So N1 is the element I, the first node, and N2 is the element I, the second node. So what this will do is, in the first time in this loop, it will read, okay, the nodes are 0 and 1, so N1 and N2 will take values 0 and 1, and I will go and get the corresponding x coordinates and do all the calculations. Second time in the loop, it will get me N1 and N2 is 1, 2, so nodes 1 and 2, so then N1 will be 1, N2 will be 2. With those, I will go and get the x coordinates, calculate the length, the stiffness, etc. And then the third time in the loop, element is 2, 3, so N1 is going to be 2 and N2 is going to be 3. And with that information, I can go and read the x coordinates, I can calculate the length, and so on. That's pretty much it for calculating the element stiffness and element force vector. And I can run this, and then I'll print it. I'll just print here. I'll do a few prints, then I'll comment them, but print element, and then I'm gonna print I, and then I'm gonna print made out of nodes N1 and the N2, so we'll print different values. Then I'm just gonna print here KE, print KE, and print FE, print FE. So let's run that, and I made a mistake. Elements is not defined. Okay, this should just be elements. Did I still not name it correctly? There we go. All right, so what you can see is the first time in the loop, so element 0 is made out of nodes 0 and 1. Basically, I'm reading in the first row of that array, right? And then it calculates what the stiffness matrix is for that element and what the force vector is for that element. Then element 1 is made out of nodes 1 and 2. It calculates the stiffness matrix of that element and then the force vector for that element. And then the third time in the loop, element 2 made out of nodes 2 and 3. This is the third row of the elements array. Calculate the stiffness matrix and the force vector. Note that the stiffness matrix is the same for elements, and that makes sense because all the elements have the same area, the same Young's modulus, and the same length. So it really makes sense that these are the same. But all the force vectors are different, and that makes sense because I'm integrating B, the force vector, and B changes, so it gets bigger as you move from x equals 0 to x equals 2L. So it makes sense that these numbers should be getting bigger. So 0.03, 0.07, then 0.14, 0.18, 0.25, 0.29. All right, so I'm doing those calculations. They should be correct. I'm gonna comment out all the prints. Now, if you go back to my notes here, so we have a definition of KE for every element, FE for every element. I got a loop of elements, compute those two. And then what do I need to do? I need to assemble into a global K and a global F. All right, so I need to initialize the global stiffness and force vectors. So K, what is the size of K? K is the size of the number of nodes times the number of nodes. So I'm just gonna do a node and node. And the force vector is just a vector of number of nodes. All right, so that's just with zeros. And then here I'm gonna do the assembly. So assemble into global. So I need to add to the correct entries of K, I need to add the KE, right? So for and for F as well, I need to add to F the corresponding FE. Let me put the F first. Right, so I need to do that. But which entry of F I should add the entries of FE? And I will replace this with a loop, but let me do this first with a loop. So, for example, the first entry of the force vector, where should it go in the global force vector? If you remember how we do the assembly, that I don't have I don't have it illustrated in the slides, but the first entry should go, because I ask you to put the global node labels next to the stiffness matrix and the force vector. So 0 should go to N1. So that's basically all I need to know. So 0 goes to N1, and then obviously I have two entries, right? So I will need to do both. So 0 goes to N1 and 1 goes to N2. Now for the stiffness matrix, I have 4 entries. So 0, 0 goes to where? Goes to N1, N1, because 0 goes to N1. So the first local node goes to N1, and then all 4 combinations, right? So 0, 1, for example, goes to N1 and 2. 1, 0 goes to N2 and 1. And then 1, 1, which is the last entry of the element stiffness matrix, goes to N2 and 2. All right, so that is the assembly. Now, this works. You can replace this with a for loop. So let me comment this out and show you how you can replace this with a couple of for loops. So let's just say manually, and then with for loops. I need to loop basically. Let me use a different, let's not repeat, just be careful to not repeat the I here. So for Ni in range 2, so that will just take values 0, 1. And so I need to do one thing. So let me just say nodes E, N1 and 2. So what I'm gonna do, or what I'm doing here, is I'm gonna put this N1 and 2 into an array so that I can read either the entry N1 or the entry N2. You can also just go and repeat sort of what we are doing here, but I'll do it like this. So for Ni range 2, F of, and then actually let me just say, should I say Ni? Well, that's okay. So here I need nodes E and I. So this is going to be either N1 or N2 equals, and you can use plus equal. Plus equal is basically the same as repeating it on the right hand side. It just adds to it. F E of Ni. So here this is 0. When this is 0, nodes of 0 is N1. When this is Ni is 1, nodes of 1 is N2. So it's basically, it's really exactly the same as this. But with, I guess in this case, it will save me a line. So I'm gonna do this. And so K of nodes E and I, nodes E and J, plus equal Ke and I and J. Again, these two for loops, now Ni and Nj, will do basically these 4 lines. So I mean 6 lines here, 5 lines here. So I really only saved 1 line for this particular problem, but in 2D or in for quadratic elements, for example, you can imagine even in 1D quadratic elements, there's 3 entries of the force vector, so this would be 3 lines, and there's 9 entries of the stiffness matrix, so this would be 9. So I would have a total of 12 lines to do the assembly manually, because I would need to do for every entry of the force vector and for every entry of the stiffness matrix. Whereas this loop would be exactly the same for the quadratic element. Like this is repeated, because the only thing that would change for a quadratic element is I would have in 3, I would have 3, and I would have 3, but the structure of the code would be exactly the same. So you see that, you know, as you increase the degree of the element, or in 2D, for example, this will be very, very, very similar. Whereas for if you were to do it manually, then you do have to write more lines of code. So, you know, in this case, it saved me 1 line, but yeah, it saves you more if you go to more larger problems. All right, that's it. So out of this, when I run this, now I have a stiffness matrix and a force vector. So F is the global force vector, and K is the global stiffness matrix. Right, so I have my global force vector and stiffness matrix. I'll print them. So print K, and just print K, print F. All right, so I have, I'll just print it. All right, so I have F, K and F, and now I can solve my system, right? So now I need to solve my system. Let me just change again this. So solving the system, we are going to do matrix partitioning. So what does matrix partitioning mean? So we need to find the submatrices. I named my first node is the one with essential boundary conditions. So the first row corresponds to that node. So the naming of the nodes is such that the first node only has the essential boundary condition. So we can partition with respect to that node. So that just means, what is the number of essential boundary conditions? It's just 1. And so what we're going to do is we're going to have this KE. I've done this one before, but KE is the submatrix that only has this number. I know it's just a number, but we're going to get it as an array because Abacus will like that. So I just need to do this. So this will subtract the portion of the matrix that goes between 0 and the number of nodes with essential boundary condition. And again, this is just going to be this number, but it's going to look like an array. Even though it's a number, it's going to have the square brackets, right? So that's KE. Then I need KEF. KEF is this matrix right here. I cannot select it, but it's basically either 45, 0, 0, and I have a mistake because I just noticed that the stiffness matrix should be symmetric. So this should be minus 45, this should be minus 45. So I missed a minus here. Yes. Okay, so I missed this minus here. Okay, now this looks correct. So I was going to say KF. KF is either this 3 right here or this these three down here, and depends on which way you do it. I'm gonna use the one at the like this -45, the vertical one. So that's K, and so in terms of rows, I need to go from NBC to the end, so to end node. And in terms of columns, I need to go from 0 to NEBC. And then finally KF, that's the submatrix that is this 3x3 corner here. So that one is K, and then I need to go from the number of EBC, so from 1, not from the beginning node, from 1 to the end, which is end node, and same for this, so from 1 to the end. And let's print them. So K E, and we can print it KE, we can print KEF, and we can print KEF, and we can print KF, print KF. So you see that KE is just the single value here, but it's a matrix. This is just a matrix with a single number. KF is this column right here, and KF is the 3x3 that is left on the corner. All right, so I have partitioned my system, and then if you recall what the solution is, so the solution should be UF equals, just put it, solution is UF equals KF inverse times what is it going to be? I'm trying to see. So K multiplies U, and then the U, there's the U known, the U unknown. So it's gonna be KEF times that. Okay, so it's minus. So this is gonna be FF minus KEF times UE. That's what it should be. I've done this in class. So the UF is the KF inverse times all the forces that are applied to these free nodes minus KF times the known boundary condition UE. Now in this case the known boundary condition is 0, so UE is 0, so this term will go to 0, right? So in this case the known displacement is UE equals 0, therefore this term is just 0, so no need to worry about it. The other thing is, what do we do with FF? So what is FF? I haven't done FF. For the force vector FF, I need to partition the force vector F and add boundary condition, add force boundary condition. This is very important. I didn't do, I'll put it in bold. So right now my force vector F that you see here, that one is just the body force. So this one still doesn't have that that extra traction at the end, right? So I still need to add that one. So I need to partition. So FF is going to be out of the whole body force. I still need to partition the same way that I partition all the other ones. I need to go from NEBC to the end. right? So only the first force vector I ignore. I just use the last 3 because that's corresponding to the free nodes. So I do that, but then I need to add the boundary condition, right? So and then add the traction boundary condition. So I need to know where to add it. Now that's basically which node has the traction. So the node that is at 2L, in this case my last node, should have this times the area would be the force. So it's just minus CL L square. That's going to be the force, and that's going to be applied to the very end. This minus 1 just says the last. So for this mesh, the node with the natural boundary condition is the last one. So add the force to that last node. In Python, you can access with -1. All right, so that will partition and add the force. So that you can already see that this is this should be the third to last, second to last elements from my force vector, and then the last one is 0.29 minus the traction. So that's why it's negative. All right, so now we can solve. Now I just need to do this, right? So I just need to do solve. So I just need UF equals mp.linalge.solve KF times FF. And that's it. Like I said, here this one doesn't matter because UE is a 0, so I'm not even gonna put it. And so that's it. So this UF, and so I just print it. That UF should be the solution. And hopefully I did it right. I have it complete here, so we can check if I did it correctly. This should be correct. So 1.02 10 to the minus 7, 1.56, and 1.11. Let's see if I did it correctly. Yes, that looks the same. All right. That's pretty much it. Let's say I want to plot it. Plot the u and the derivative du dx, because I do want to see you plot things. Note that this uf only has the last 3, so I need to get I'm gonna call it node u, which should have the ue. Okay, let me just say first create an array with all the nodal u, so the ones with essential boundary conditions and the ones I just solved. You can do that with in NumPy. You can stack things, so you can do I don't know if it is H stack or B stack, but we can just check. So I need to do MP array 0, so the one with the essential boundary condition, and UF. Let's see if this looks correct. If it doesn't look correct, I'll use VStack. This looks correct. Okay, so now I have a vector that has the node with essential boundary condition is 0, and then the other solution. All right, so I have that. Now I can plot. How do I plot? I need to plot over each element, right? Because I can only plot, and this is part of what you did already in the other Python lab. So for plotting, you can reuse the code, but I'll do it from scratch here. You need to loop over elements because you can only plot inside of each element. So for plotting, loop over elements, plot for each element. So I'm gonna have another loop just like before. Loop over elements. I'm gonna actually reuse some of the code here. I still need this, so I'll do this. I don't have the shape functions. Okay, for plotting I need the shape functions. So let me also put here. So for plotting, need shape functions. I'm gonna use the shape functions in terms of x. I can do either way. I'm gonna do both. I don't know how long this video is already, but I'll just do both. And yeah, let's just do both. So let's do the functions in terms of x. So when I do them in terms of x, I need to pass the beginning and end of the element, and then return, so x minus x2e over x1e minus x2e. And so that's n1 and n2. And n2 is just going to be x minus x1e over x2e minus x1e. And I need the derivatives, so dn1 dx, again x param, and then I'll just copy these. And so here the derivative, this is just 1 over this, and then let me copy this, and so I want dn2 dx, and then the derivative of this is just 1. That's it. So now I have my shape functions, the derivative of the shape functions. Let's just do it with these ones. So I'll do it with these ones. So going back to my loop over elements. So I have my loop over elements, and now I can, what do I need to plot? Plot u of x, which is the sum of ni times ui, right? And then plot du dx, which is going to be the sum of dni dx times the ui. All right, so u of x. Now what x, u is a function of x, right? So that means that I need to pick some x to evaluate. And in order to plot, what I need to do is I need to have a bunch of x's. So I'm just going to do a linspace between x1 and x2. And then how many you want? I don't know, 50. So this will create values of x between x1 and x2, 50 of them. And I'm going to evaluate u at all of those x's, right? So for that, I'm just going to do n1. And actually, I also need to define these params, x1e, x2e. So I'm going to evaluate the first shape function at all those x's, and I need to pass these parameters, times the u at the beginning of the element. So this should be u1. But what is u1? Well, actually, let me put it like this, and then I'll tell you what u1 is. Let me call it u1e, so that it's a little bit clearer. And here I'm going to have u2e. Okay, perfect, like that. And then du dx vec equals, and then very similar, but instead of this, I'm going to use the derivatives. And so here, everything is defined except u1e and u2e. So that one is going to look something similar to the way I read the x1 and x2e. Very, very, very similar. I need to also read the nodal u values same way as I read the coordinates of the element. So u1e is just gonna access from the node u the n1, and u2e is gonna access from the node u the n2. And now that should be correct. I just need to plot it. So let's just do plot xvec uvec, and then plot xvec du dx vec, and chase my errors. How did I? It's for the derivative, really? Yes. Okay, I'll change this a little bit, because you can see that when I evaluate the u, I am passing a vector of x, and I'm returning basically a vector of x, because it does everything sort of vector-wise. But here, even though I pass a vector, it's returning a single scalar. So I need to change this so that it's np1s of the size of x. Yeah, so hopefully this is correct. Wait, mp1s, and then I need one more of this. So len x, and then like this. Okay, so I need this in here as well. Alright, so now it will work. Okay, I actually don't want them in the same plot. This is correct, but I will plot them into two separate ones. So I'll create subplots, and I forgot how to do that. Please let me. Yes, I did it here. Okay, so let's just copy this line. I just need two subplots, and then here, instead of doing PLT plot, I'm just gonna do AX1 plot and AX2 plot. And all this is doing is in the first subplot, it's plotting the uvec, and in the second subplot, it's plotting the derivative. Yeah, and so this is the solution for 3 elements, the du dx, and this is the derivative. You can add labels. I have it here. By the way, I think this hopefully should already be on. There should be already a solved Python lab in the Brightspace. So let me just copy all of that, because I think it's the same problem. So the annotations should be the same. Well, because I don't know what this is. Oh, this is the exact solution. Well, let me comment that out. Hopefully the rest works. Yes. So here, this is u h of x du hx, and we have an exact solution. So I'm just gonna copy that. I'm not gonna type that in, but there is an exact solution. You can see in the textbook there is an exact solution. So I can actually evaluate the exact solution, and I'll just do that here. This is to plot the exact solution, so I'll alright, so this plots now the finite element solution and the exact solution. So you can see, obviously we do better for the displacements because our function is piecewise continuous. So the finite element solution is this blue, orange, green one. And then the derivative, again, the finite element solution is this blue, orange, green, and the exact solution is this quadratic function. So you can see that obviously we do much better at the solution because it's continuous. For the derivative, we have a piecewise constant, and it's okay in that, you know, for the first element, the solution is, you know, it's high. Then for the second element, it's a little bit lower. For the third element, it's a little bit lower. So it overall follows the trend, but it's not as accurate. I think that's it basically for this problem. I wanted to just show one extra thing. I don't think I'm gonna solve the other problem, so I'm not gonna solve this problem right now because I think this video is quite long already. But this one is what I did for homework 3 last time I taught the class, so it should be on the Brightspace. So if you are curious about the solution of this one, you can check the Brightspace. The Python solution is also there, so I'm not gonna do it now. Instead, the one thing that I wanna do is I'm gonna plot the same thing, exact same thing, but with the mapping to the xi. So let me just do it here. So plot exact same thing, but using the map to xi space. And so the thing that I need for that is need shape functions and derivatives in terms of xi. So I'm gonna copy these ones, but I'm gonna change them a little bit. So first I'm gonna copy these ones, but now I'm gonna say xi, and actually let me rename this as n1 xi so that I just use a different name. So these ones take xi. I don't need the parameters. Why? Because the first element, the first node is always -1, the second node is always +1, so this is gonna always be like this. For the second one, again, I don't need the parameters because I already know that the first one is -1, the second one is +1. And then for this one, the derivative, again, I don't need the parameters. I already know that this one is -1, that this one is +1. Then this is np1's length xi, and then xi, and this again xi. And then I already know that this is -1, this is +1. So these functions are functions of xi and the derivatives with respect to xi. Perfect. Okay. So for plotting, I'm gonna follow more or less the same as here up to this point. I'm still gonna loop over elements. I am going to get the nodes. I'm gonna get the coordinates, and I'm gonna get the nodal values. But here is use iso parametric map to get x of xi, and use xi shape functions also for u. So instead of doing u as a function of x, I'm gonna do u as a function of xi and x as a function of xi. Essentially, I'm doing this. So x as a function of xi is the sum of the shape functions, which are now a function of xi, times the nodal values, and u is the sum of the shape functions times the u values. And I'm just using ni xi just to denote that these are shape functions in terms of xi. So maybe I should just say ni in terms of xi, and I in terms of xi times ui. So that's what I'm doing, and then I'm just gonna plot basically x comma u. But you see that now things are function of xi, so what I need is a xi vec. So I need a linspace for xi vec. Now xi always goes from -1 to 1. So it's the linspace between -1 and 1, and then with that I'm gonna evaluate both x and u. So x is gonna be n1 evaluated at that xi vec times x1e plus n2 evaluated at that xi vec times x2e. And then for the u is going to be the same, n1 evaluated at the xi vec but times the u1, and then this times the u2, and then I'm going to plot it. So I'm just going to do x1 plot. I'm still plotting u as a function of x, even though I only have x as a function of psi and u as a function of psi. I can still plot xu. So let's do that, and you see that the plot that I get is the exact same plot that I was getting last time, right? So in the end, I'm still plotting x and u. It's just that now I'm parameterizing x and u as a function of the psi. For the derivative, a little bit tricky. There's one thing for the derivative that you have to be careful with. So the x is the same, well, almost the same. So the x is the same. Now, what is du dx? Well, the problem is that I have u as a function of psi. So if I do the sum of this sum would be the derivative of u with respect to psi, not with respect to x. So I need chain rule. So I need that times, I need chain rule, times the d of psi dx. I don't have d psi dx, but that is the inverse of the Jacobian. So what is d psi dx? How do I get that? Well, I know dx d psi, which is this sum of this sum, which is the Jacobian, right? So then d psi dx is just the inverse of that. All right, so I need to calculate the Jacobian inverted, and then I will be able to do this sum times the inverse of the Jacobian. So again, because I have u as a function of psi, but I want du dx, if I just do the sum of the derivatives with respect to psi times u, I am getting derivative with respect to psi, not derivative with respect to x. So I need chain rule, and I need d psi dx. And this is the inverse of what I have been using for integration. For integration, you need the other one. You need the dx d psi, right? And because you're going from the x space to the xi space to the integral, and here we are going from the derivative with respect to psi, but we want to get it with respect to x, so we need the inverse of the Jacobian. All right, so let's do the Jacobian. Right? What is the Jacobian? The Jacobian is basically the derivative of x with respect to psi. So d is this. So the Jacobian is the sum of the derivatives with respect to psi times the xi. Right? This gives me basically dx d psi. This is what I'm getting, dx d psi. I'm just taking the derivative of the isoparametric map. I'm just taking the derivative of this basically. The derivative of this is the Jacobian, and then I need the du dx. Now du dx is this times, so it's that times the inverse of the Jacobian, which in this case is 1 over j. And now I can plot it. I'm still going to plot x, but against du dx. Like. And this should be the same as I have here. So I just wanted to show that. I'm still going to plot the, I'm going to add the exact solution, and I'm going to add the annotations. But you can see that I plotted the same thing, the same finite element solution, the same derivatives. But in this second plot, I'm doing everything with the shape functions in terms of psi. For your homework, you don't need to do this. For your homework, you can do everything with x. So you can just use the shape functions with respect to x. This is just an extra. All right, so that's about it. Yeah, good luck with homework 3, and then I'll see you on Monday.